So, so right now, what we're going to do is there's some notation stuff that we've got to kind of knock out, so that we can actually start talking about probability and everybody be on the same page when we start using that notation. So that's what a little bit about today is going to be. One thing, we talked yesterday. We did that simulation about the die or the coin. Not all coins are fair coins. Okay, some coins are, one side is maybe heavier than the other side, so that it lands down more often. In the event that we're using a device like that, for flipping a coin for who gets the football first in a football game, we would want to make sure that those are fair. Okay, so the way that they're designed kind of takes into play there. Talk about dice. If I'm a casino, I want to make sure that the dice are fair, that one side does not end up landing down more often than the other sides. Does that make sense? Okay. And you can kind of think maybe about the procedure of that, how that happens. If you think about dice, one face has 6 kind of dimples drilled out of it, right? Another face has 1 dimple drilled out of it. There's an unequal weight distribution there that has to be kind of taken into account when then trying to create dice so that they are fair. Does that make sense? Casinos, obviously, if I'm playing Yahtzee at home, I don't really care about that, right? But if I'm a casino and those dice are being rolled hundreds of thousands of times a day for hundreds of thousands of dollars, I would want to make sure that in the long run that the player is not benefiting from unfair dice. Yes. I've never been to a casino. I'm not really into making money and then wasting it. But I'm pretty sure that's how they are done. They're not, those dice aren't beveled out. When we talk about probability, we're going to talk about 2 types of situations, 2 types of outcomes. They're going to be or events and events. Okay. The word or refers to, if you had me for geometry, we talked about this, but we talked about a little bit more detail in college algebra. You guys remember talking about or being the word union? Okay. I sense the sarcasm. Oh, okay. That was the day you were awake. So if I say something like this, and I get this graph, and I call this a set of solutions, and let's say that's A, and this is a set of solutions, let's call that B, and I ask you to A union B, that means I have to have all of A along with all of B in my solution. Does that make sense? A or B. It means my solution comes from A or it comes from B. So that's kind of what's going on right here. Whatever these events are, event A has these individual outcomes, 1, 2, 3, 4, and 5. Event B has the outcomes 4, 5, 6, 7, and 8. Okay? If I want to know the probability of, let's say, A or B occurring, then I need to know what is A or B. It's everything from A along with everything from B. Does that make sense? Okay. Now, situations that take place, we call it the union, obviously, but situations that take place are something like dealing with cards. Now, first period said that they are lacking in their card knowledge. Okay. Yeah. If I ask you what's the probability of picking a red or a spade, okay, if I asked you what that probability was, okay, you have to know that or means I'm doing all of the reds along with, so my outcomes, my likely outcomes that match to my event, so my numerator, my probability fraction, has got to be all of the reds along with all of the spades. Does that make sense? That's what the or is referring to, okay? Which basically means if I'm taking all of the reds along with all of these spades, I'm adding. Does that make sense? Okay. So how many are there? It'd be 3/4. Okay. So there's 26 reds. Okay. There are 13 spades. Okay. So that's what? 39 out of 52. That reduces to then 3/4. But we have to understand what that or means. It's all of these along with all of those. Okay? And events means it's the overlap. Okay? Going back to like a graphical thing. Okay, this was the symbol that we used. Okay? We talked about it as an intersection. But if I had this number line starting at like -2 going to 5, and I said I have those solutions and those solutions, and I said, what is the intersection or the and for the top graph and the bottom graph, the top red one and the bottom red one? It would be where they're overlapping between -2 and 5. Does that make sense? So it's where they're shared. So that's kind of a connection that we've made, maybe in graphing in Algebra 2, college algebra, geometry, and now we see a connection into probability. Okay, and what we're doing here right now is kind of it's structured kind of like set theory, which is a branch of mathematics that just deals with collection of objects and how we can take subsets and look at the or the union, the intersection, that kind of stuff. But it's very important for probability. So if I say let A equal 1, 2, 3, 4, 5, and let B equal 4, 5, 6, 7, 8, and I said what is A and B? Well, that is the objects that are in A, and they are also in B. Does that make sense? Okay. So if you struggle to remember which one's which, okay, and hopefully you realize there's two qualities there that have to be met. Two conditions have to be met. Have to be in both at the same time. I've always remembered, okay, what does and mean? The overlap. I remember that one, and then that by default tells me what the or the union one is. Does that make sense? Okay. So now the question is, if I say what's the probability of getting a red card and an ace in one draw, what is it that now we have to think about the sample space being all 52 cards. Now, what events or what outcomes are aligned with the events of red and ace? How many of those cards are red and ace? Just the two, right? Okay. Hearts and diamonds. Does that make sense? Okay. Now, something that we talk about, and we'll get into a greater explanation of this and analysis of this, but they're called mutually exclusive events. We're looking, one of the things in stats and probability is that we want mutually exclusive events. And mutually exclusive events are two things that cannot happen at the same time. Because that makes probability a little bit easier. Meaning, if I flip a coin, landing heads and landing tails are referred to as mutually exclusive events. They cannot happen at the same time, right? Okay. But if I roll a dice and I say I want to get a 6 or a multiple of 2, a 6 or a multiple of 2, can those happen at the same time? Yes, because if it lands 6, that is 6 and it's a multiple of 2. Does that make sense? So those would not be mutually exclusive. And that makes a formula a little bit, or a probability a little bit more difficult to determine. With cards, one of the common questions we ask, what is the probability that we get a ace or a red card? Can those happen at the same time? Yes. So those are not mutually exclusive. Okay. Another word for mutually exclusive, and again, we'll talk about this. There'll be notes that have it written down, is the word disjoint. Okay. So those are not mutually exclusive, or they are not disjoint. Okay. Meaning, I can have an ace that is also red. Does that make sense? So here, if I say, well, how many aces do we have? So the idea is that this is going to be the probability of an ace plus the probability of a red card. Does that make sense? Okay. How many aces do I have? 4. How many red cards do I have? 26, right? Okay. Now, The issue is right here in your probability, did you count in the ace of diamonds and the ace of hearts? Those are two of your four aces, right? In this 26, did you count in the ace of diamonds and the ace of hearts? Because they're both red cards, right? So do you see how those two cards, they only show up twice in the deck, but in this probability, we've shown them showing up collectively 4 times. Does that make sense? Okay. So we need to remove, we counted them both here once, we counted them both here once. We only want to count them once overall, right? So I need to remove the cards that are red and aces. Does that make sense? Okay. So when I say probability of A plus probability of R, that's if the events cannot happen at the same time. But if they can happen at the same time, then we remove the probability of A and R. Which cards are aces and red? Well, there's 2 of them. Okay. So that's the purpose of understanding what the or means and what the and means. And again, these formulas will become more, we'll have sections that we target these and we investigate them and analyze them with a lot of different examples, and they will become easier to remember and deal with. But you have to always investigate, what does my sample space look like? What do they mean by or? Are my events independent or dependent? Okay, talking about independence and dependence. If I flip a coin and it lands heads, and I flip a coin again, flip a second different coin, did the heads that landed first, is that going to impact the second coin and how it lands? No, they're not tied together. If I give you a deck of cards and I say, pick a card out, put it in your pocket, and now what's the probability that you pick an ace on the second pull? Does it matter what you pulled the first time? Yeah, because now the second one, you're only picking out of 51 cards, so your sample space changes. And what if that card that you picked first and put in your pocket was an ace? So now in the second pull, you've only got 3 aces to pull out of the 51. Does that make sense? So what's that? So what? Pick from the top.
Yeah, they ask you to pick from the top, and like the card you pick is the card they want you to pick.
Well, I mean, so you got some of that stuff that could kind of create bias, but like when we do those things, like we're assuming that the cards are fully shuffled, and picking the top one is exactly like picking the bottom one. It's exactly like picking the third one. Exactly picking the 18th one. They're equally likely to occur. That make sense? But you're right. The power of suggestion, which we've talked about in statistics, can be something that might alter those probabilities. All right. So complement. Where have we seen complement or the word complementary before? In one of my math classes that you've all taken. Geometry. Talk about angles. And so if I have complementary angles are 2 angles that add to 90. Okay. So the geometric definition of complementary angles has that component of 90 degrees, right? And if I tell you have one angle that's 20 degrees, you automatically know its complement is what? 70. Because you have one and you have the total, you can subtract them to get the unknown, right? So when we talk about complements all across mathematics, it's that idea. Now the sum might not be 90. When we talk about complements and probability, what's the sum that we're looking for in all probabilities? If I have, go ahead. What should all probabilities add up to? 100%, or 1, right? Okay, is that what you're going to say? Okay, so if I tell you that it's a 30% chance that it's going to rain today, the complement of that is, in probability, is 70%. That's everything else, right? And now what is also nice about complements and probability, if I tell you it's 30% going to rain, you know that it's 70% not going to rain, right? You know it's the 100% opposite situation. Okay, the complement idea allows and makes probabilities easier, or calculations sometimes easier to deal with. Okay, the notation that we use, or at least this textbook uses for a complement, if I say A is the event, so Usually I'd be like, what is the probability of event A, something like that. Then the complement would be probability of, and then they say A, and they put that apostrophe up there, and we call that A prime. Okay. You've got a choice. You know, when we're reading this and doing these problems, you might see somebody say, what's the probability of A prime? Or they might read that and say, okay, we're talking about probability. That's that complement notation. They'll say, it's the complement of event A. So they'll say, what's the probability of complement event A? Some textbooks will say, instead of A prime, they'll do this. A little C up there as a superscript, stands for complement, right? Some textbooks will say A with a bar over the top of it, or whatever the event is, and put a bar over the top of it. And that's just notation for complement. So all those things are various ways you might see that. And the reason I show that, obviously, our textbooks use the A prime, so that's what we're going to focus on mostly. But if I, find a YouTube video and post it for you to watch, and they use A bar, okay, my hope is that you make the connection that is fine to do. Okay. So if by definition probabilities should add up to 1 and event A and the complement event A are opposites, then we should say that we have this formula: probability of event A plus the probability of its complement is equal to 1 or equal to 100%. Okay. So that allows us to do some just short arithmetic there with that equation and get the idea that the probability of an event is 1 minus the probability of its complement, or the probability of a complement is equal to 1 minus the probability of the event. Okay? You'll see as we do some examples here in a little bit the purpose of this. Okay? It should make things a little bit easier for us to calculate. All right, so what's complement of tails? Heads. Okay, what's complement of weekdays? Weekends. What's the complement of 35% rain? 65% what? So you guys, so we're just doing like skimming the surface of probabilities. Like there's probability that involves a lot of calculus, and obviously we don't know that calculus yet. So this is like taking, like if we talk about our algebra, we didn't just take algebra in high school, right? We took algebra 1, algebra 2, college algebra, right? So algebra 1 just kind of skimmed the surface, and then those courses got deeper into it, right? So when we take probability statistics first course in high school or college, just skimming the surface, and then we can get into more questions like that using some calculus and stuff like that. 7. It is. Yes. Say what? From this we get. Oh, this didn't print? Oh. Well, you might want to write that down. Sometimes, like, when I don't know, yours printed that way? Yeah. It doesn't show up? Where'd you get that at? Is that in the email?
Yeah. Yeah, maybe you should do the hangout one. Okay.
That's the same file. Like, that's weird. But when I insert formulas, sometimes I use different, like this. I believe I was using the word, like insert equation tool that it has, and sometimes that thing's screwy. Sometimes, like yesterday, I was printing off a stats test. I think it's for Kenna, and it wasn't printing off the graph and stuff. It was weird. So I apologize for that. But all right, here's a couple examples, a couple questions. So suppose you roll 2 dice, and you're going to analyze their sums. Okay. So I have 2 dice, whether I roll them independently of one another or I roll them both at the same time. Doesn't matter. Okay. So what is the probability that the sum is 7? Huh? Okay. So, What are you doing? You're saying 6 and, so 6 and 1, 2 and 5, 3 and 4, 4 and 3, 5 and 2, 2 and 5, 6 and 1, 1 and 6, right? Okay, so how many was that? It's 6. It's six outcomes. But now, what are all my possible outcomes?
3, 3.
Okay, so you get 4, 4, 3, 3, 1, 1, 2, 1. But I had 2, 1. Did I have 2, 3?
Yeah.
Okay, so it's hard. So you said 36. Okay, because basically you've got, it's really the fundamental counting principle. You got 6 things that can happen on the first roll, 6 things can happen on the second roll. 6 times 6 is 36. But what happens and is hard with probability is, in order to answer our probabilities, we need to know what our sample spaces look like. Okay. With rolling dice, this is the best way to kind of structure, because if we create a table, it systematically makes sure that we get all potential outcomes that should show up on those dice. If we're just trying to wing it from memory and say, okay, well, 1, 1, 1, 2, 2, 1, 2, 2. I might miss one, right? I might count that I've got 35 options, or I've got 34 options, or something like that. Or if I'm just trying to count, 5 and 2, 2 and 5, 3 and 4, 4 and 3, I might not get all. I might skip one. Okay, but if I've got it written down in front of me in a structure, it's going to be easier to recognize. So across the diagonal here is where we get the sums of 7, right? And that is like Riley said, that's the most frequently rolled combination or sum. Okay, because if I look across the diagonal, that's the longest diagonal, right? Okay, so, well, I guess we could say, yeah, I'm sorry. So that is the longest. Okay. Now, if you play like I think I'm not a big gambler, like I said, but roulette, I believe you win if you roll 7s and 11s. Okay. What? Craps, that's what it is. Okay, so 7 and 11. You guys gamble more than I do. That's terrible. Where do you get your money? Huh? Craps? I was watching. It's totally off subject, but I was watching the news, and they had one of the senators on. His last name's Crapo. You imagine he got made fun of a lot. And then they try to like fancy it up, like that's not how you. It's like Crapo or something like that. Like no, it's Crapo. All right, so we got 7 possible outcomes that align with this sum of 7 out of 36 total, right? Okay. What if I asked you, and this is the idea of dealing with complements, or the benefit of dealing with complements. What if I asked you, what is the probability of not a sum of 7? Not a sum of 7. And that's kind of nasty to write. So a lot of times what they'll do is they'll use this little tilde, that means not, in set notation. And then they'll say, like, sum 7 or something like that. So if I did that, wouldn't it be easier? It is 5 out of 6, okay? But not, so basically what we would be saying is, okay, well, if it's not going to be 7, then it could be that one, 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 and I could count them all up, right? And I'm going to get how many? Huh? Okay, so 30 out of 36 are going to be not 7, right? But is it a pain in the butt to go through and count all 30 of those, make sure I've got them? Wouldn't it be easier to know what my total is? 100%, right? Or 1. And subtract the probability that it is a 7 or is sum to 7. So wouldn't that be 1 minus 1/6? Does that give me the 5/6 that would then be not a sum of 7? That makes sense? So if I can, remember what complements are, if I know one thing, okay, and if 30% that it's going to rain, then the complement is not rain, okay? It's always the negation of the event. So that's a benefit to us. Let's do another example. Let's say Let's say we go back to the probability that let's go to a deck of cards. Pull let's go a spade or a heart or a diamond. Okay, so pulling it, can a spade ever be a diamond? Can a diamond ever be a heart? No. So these are mutually exclusive. So what's going to happen here is our probability would be probability of spade plus probability of a heart plus the probability of a diamond, right? Okay, what's the probability that I get a spade? 13 out of 52, right? Probability of heart? 13 out of 52. Probability of a diamond? 13 out of 52. So can I add those together and get 39 out of 52, right? And that reduces to 3/4, right? Okay. Now, what is the complement of that event? Probability of getting a club, right? And probability of getting a club is 13 out of 52, right? Or 1/4. Okay. So could I, rather than doing all of this work here, could I have just said 1 minus the probability of getting a club is the exact same thing as the probability of getting a spade or a heart or a diamond? You see that the calculation there is simpler? And now that's a very basic, kind of elementary example, but you're going to find out eventually when we start getting into more complex probabilities, it will be sometimes and definitely impossible to get the probability up there at the top without using the complement concept. Okay, just based on the information that we have, that we're privy to in those types of probabilities. Is that all right? Do we see at least a benefit or an alternative to finding the probability? Okay. Already did that. So fair die is thrown. What's the probability the score is not a factor of 6? Not a factor of 6. Okay, so I don't like questions that use the word not. Okay, so what I'm going to do is I'm going to say, what is the probability that it is a factor of 6? Okay, so if it is a factor of 6, what are my factors of 6? 3, 2, 6, and 1, right? So probability that I do have a factor of 6, rolling a die, would be 4 out of 6, right? Okay. So then the probability that it's not a factor of 6 would be 1 minus the probability that it is a factor of 6. Which would be 1 minus 4/6, which becomes then 2/6 or 1/3, right? Okay. Now, if that's the case, 2/6, what are the two numbers on the dice then that are not factors of 6? Huh? 4 and 5. Okay. Now, you could have maybe decided that because you know the sample space is pretty small for that situation, right? But regardless, we have an alternative way of finding that probability. 2 fair coins are tossed. What's the probability of at least? So questions that say not and questions that say at least, I think, best set themselves up for using the complement rule. Okay. In regards to the situation, so when I say at least, I'm setting the floor, right? Okay, I'm setting the bare minimum. Okay, so I could have more than 1, right? Okay, so when that happens, when we see at least, it basically means that we're adding probabilities up. So when I say the probability of at least 1 head, that is actually going to be equal to the probability of 1 head Okay, or two heads, right? Does that make sense? Okay. Well, if these are independent events, which they are, it's going to be probability of one head plus then the probability of two heads. Which we can do that. Okay. You're going to find out later on when our sample space is more confusing than just flipping two coins. This strategy is not preferred, and we like to use a complement strategy, but we'll do it this way first. But now I need to know what my sample space is. If I want to look at my sample space for flipping two coins, and this is going to be something that it's kind of weird the way our text does this. We're going to have to develop sample spaces using tree diagrams, but our text doesn't really explain that approach until the last section of this chapter. So hopefully by the time we get to that last section, we can kind of zoom through that section because we've seen it enough from 3.1 to 3.4, and I've explained it a couple times. But what a tree diagram is that we start from a basic point, okay? And you emanate from that point with these branches, okay? And each branch represents a particular outcome or a possible outcome, okay? So right here is going to be our first flip. What are my options for my first flip? Heads or tails, right? Those are the only two things that can happen. Now, from each one of those individual outcomes, if the first flip landed heads, what could the second flip land? Heads or tails again, right? Okay. And then if the first flip landed tails, the second flip could have been heads or tails again, right? Okay. So now here's the way that this works and how we develop our sample space. You follow these branches to the end, okay, from this point all the way till it dead ends, and you record the results that you pass through. So one of my results when I flip two coins could have been heads and heads, right? Okay. Another result could have been heads and tails. I don't know why it does that. It jumps back and forth sometimes. All right. Could have been heads and tails. Could have had a result that went tails and heads. And could have had a result that went tails and tails. That make sense? Okay. Now, you might say, well, I could have known that sample space without drawing the tree diagram, which I agree. But what if I said, what's the probability if you roll a dice and then flip a coin? Okay. What is your probability of getting a 7 and a heads? Okay. Or an even number and a heads or something like that. So now your tree diagram is going to be more kind of messy, right? But this is our sample space. Okay. Now, if I go back here and say, okay, well, probability of at least one head would be the probability that I get one head, which would be this one here and that one there, right? Plus the probability that there's two heads, which would be that one there. So I've added 3 out of how many? 4, right? Okay. Well, if I think about the word at least, so if I say probability of at least one head, okay, what would be the complement of at least one? If 1 is the bare minimum, the opposite of that would be none, right? Does that make sense? So what if I said the probability of no heads? What's that probability? That's the only one, right? Okay. So if I know this, if I understand complements, I understand the complement of at least one means none. I don't even need to write this tree diagram. I know when I flip my coins, there's only one chance I get tails, tails, right? So if I go 1 minus that chance of tails, tails, does that give me 3/4 right away instead of having to come up with the sample space and count 1, 2, 3 out of total 4? So that's another benefit then of that complement approach. Okay, we will use the complement approach a lot this year. Okay, It makes calculations simpler. If we can, like we did here, do the calculation using multiple approaches, I will. And hopefully that then opens your eyes to seeing that one is more efficient than the other. All right. Tomorrow we'll get into conditional probability. Okay. And conditional probability simply means, okay, what is the probability that I pull a red ace out of the deck knowing that I've already pulled a red ace out? Okay. Or what is the probability that we're going to have a quiz knowing it's Friday, or given that it's Friday? But tomorrow's not Friday, but tomorrow's Thursday. But tomorrow is Friday of this week, right? Last day of the week?
Yeah.
Yeah.
I mean,
No quiz tomorrow.
the week, but it's the last day of the school.
There's no quiz tomorrow. I was just messing with you.